All right, hello everybody. In this video, I'm going to present a recursive solution to the Tower of Hanoi puzzle. This is a puzzle that involves 3 pillars and a tower of discs, and the objective for the player is to move the tower from one peg to another, with the constraint that you're only allowed to move one disc at a time, and you're not allowed to place a disc on top of a disc that is smaller than it, right? Or in other words, at all times, the discs have to be stacked in this descending order in terms of size. Okay, so with a small set of discs, this puzzle is pretty trivial and not that intimidating, but you can imagine as the number of discs increases, even knowing where to start becomes kind of tricky. So let's see if we can come up with an algorithm that allows us to solve this problem without needing to think too much, okay? Now, recursion is kind of the art of taking a problem and restating it in terms of a smaller problem or set of smaller problems. So for instance, with the Fibonacci sequence, often we will define the nth term in the Fibonacci sequence as the sum of the n-1 and n-2 terms in the Fibonacci sequence. The idea being that those are smaller, simpler problems, and if we keep doing that, eventually we end up with the trivial situation in which we're looking at the first 2 values in the sequence and those are given. So similarly, with the Tower of Hanoi problem, we want to kind of, in our minds, break the problem down in that way. And a good place to start is to identify a very trivial case, which we'll often refer to as a base case, or in some cases there are multiples base cases. In this case, the most trivial situation I can think of is one in which we're trying to move a tower of 0 discs from one peg to another. And of course, that's easy. There's nothing to do, okay? So we'll consider that our base case and then move on to something more interesting and to try to see if we can discover a recursive algorithm by doing so. So let's start with the task of moving a tower of size 1 from peg 1 to 3. And of course, that's easy. We simply move that disc from pillar 1 to pillar 3, and we're done, right? No big deal. Let's get a little bit trickier. So now let's try to move a tower of size 2 from pillar 1 to pillar 3. And this gets a little bit more interesting, right? We can't move 2 discs at a time. And if we were to move the top disc to pillar 3, it would then block our ability to put the bottom disc from pillar 1 to move the bottom disc from pillar 1 to pillar 3. So that's not going to work either. Luckily, we have this intermediate pillar. Keep getting my words confused there. And by using it, we can do a bit of a swap-like function here where we use a temporary location to enable the movement. Okay, now I'm going to restate what I just did a little bit. I talked about moving discs. I'm going to try to rephrase it in terms of towers. So we're going to move a tower of size 2 from peg 1 to peg 3 using 2, meaning using pillar 2 as an intermediate. So I see 3 steps. First, we move a tower of size 1 from 1 to 2, right? You saw that step. And you notice I'm using the word tower of size 1, or the phrase tower of size 1 instead of disc. And we'll see why that's important in a moment. We're alluding to, obviously, already kind of the recursive solution here. And the second step was to move the disc from 1 to 3, and then finally to move that tower of size 1 from peg 2 to peg 3, and then we were finished. Okay, so again, just a slight change in the wording of what I did there hints heavily at how we might solve this problem in the general case. So let's move on now to a tower of size 3. We want to move a tower of size 3 from peg 1 to peg 3, again using 2. Peg 2 as an intermediary or as a width peg. But before we do that, I want to talk just a moment about perspective. So one of the things that can get in the way when we're trying to discover a recursive algorithm is that we fail to see how general in nature the problem is. Maybe we start identifying pieces consciously or subconsciously as unique when they're really not. What do I mean by this? Well, in this case, when analyzing the Tower of Hanoi problem, we often will draw it and with some kind of view like I've got here. And we'll assume this is kind of a frontal view of these pegs. And I've numbered the pegs to help me keep track of them. The problem is that we may kind of assume subconsciously that from the top, these pegs look like this, right? Where they're really in a row and there's this linear relationship between them. The problem with that is that we may then, again, consciously or subconsciously, begin to see differences where they don't exist. We might think that there's a difference, significant difference between moving a disc from peg 1 to peg 2 versus from peg 1 to peg 3, right? Just because of the order of the pegs and the differences in distance and so forth. And that kind of limits our view in terms of possible solutions, right? So it may be useful to instead adopt a different view of these pegs, one in which if we were looking at them from the top, we can see that they're kind of equidistantly placed on this two-dimensional plane, right? With this perspective, we see that there's not really a meaningful difference between moving a disc from peg 1 to peg 3 or from peg 1 to peg 2, right? And so then we start to realize that using the numbers 1, 2, and 3 is not meant to imply any kind of sequence, but rather they're just identifiers. We might have used A, B, and C, or if we'd chosen, we could have even used symbols like diamond, heart, and clubs. The idea is just to be able to uniquely talk about or explicitly talk about particular pegs and not get confused in terms of which one or which pair we're trying to address. But really, what's significant here is just that there's a peg we're trying to move from, a peg we're trying to move to, and another that we will work with to get the job done, okay? And of note here is that we could change the order of the with and to pegs, and the algorithm hasn't significantly changed, right? We've simply changed the order of the pegs. We can still get the same job done. Really, we just have to know which peg we're moving from, which peg we're moving to, and which one we're using to get the task accomplished. And it may be that depending on the specifics, which tower we start on, how many discs there are, and so forth, we may be able to shuffle things around a little bit and temporarily switch our to and our with in order to get things done during intermediate steps. And that's perfectly fine. Okay, we just have to realize that we can do that. If this seems a little confusing, I think it'll become a little bit more clear in a moment. So let's go back to this problem then of moving a tower of size 3 from peg 1 to peg 3 using 2, okay? Now, if we think back on the solution to moving a tower of size 2, we saw this notion of moving all of the discs off of the bottom disc, so I can move the bottom disc and then moving that sub tower on top of it, okay? And so visually, if we're doing this with 3 discs, we might say, okay, so I'm going to move this tower of size 2 off the top and put it onto peg 2 as my first step. Okay, now I can't actually move the discs 2 at a time. I'm limited to moving them 1 at a time. And so, of course, we're going to need to use peg 3 to actually accomplish that task. Okay, so I'm just summarizing here on a high level what I want to accomplish. I'm not showing the actual legal moves yet. But the point simply being, if I can move a tower of size 2 onto peg 2, that frees me up to move this bottom disc onto peg 3. And then I'm free to then, if I could move the tower of size 2 onto peg 2 using peg 3, then I should be able to do the same thing to get it onto peg 3 using peg 1, right? So that's just hearkening back to the discussion we just had, that there's no specific significant difference between the pegs. And so if I need to kind of shift my targets temporarily in order to get things done, that's perfectly fine. And I should feel free to do that. And so that's what I'm doing here. Now, initially, I simply used a different target, a different peg to get my sub tower off of peg 1 so I could move the bottom disc onto peg 3. Now I want to move that sub tower again from peg 2 to peg 3, and I'll just use peg 1 as my intermediary, right? So there's kind of this universal idea of moving discs and towers and so forth, not needing to worry too much about the pegs. They're not unique. So writing this down then, as I said before, we first move the tower of size 2 from 1 to 2 using 3, then move the disk from 1 to 3, which you saw me do, and then finally move this tower of size 2 off of 2 onto 3. Now, worth noting is the fact that by doing this, by thinking about first moving the entire tower of size 2 off of that bottom disk, we don't have to worry about the bottom disk. Okay, since we're not moving it at all while we're moving these other two disks, or however many there are, the tower on top, I don't have to worry about it getting in the way, right? It's the biggest disk, but it's sitting on the bottom, and so we don't have to worry about breaking any rules relative to that disk. So in essence, we can kind of ignore it while we're trying to move the tower of size 2. And so we end up with the problem that we discussed before. We already know how to move a tower of size 2 from one peg to another. We just have to recognize that it's the same problem, just with a different arrangement of pegs, okay? So, and then once we've got it halfway, then finishing the task or finishing the job is trivial. We just do the same thing just by shifting pegs. Okay, so interrupted my writing there. So again, we finished by moving a tower of size 2 from 2 to 3 using 1, and we're done. Let's try to take the discussion we've had so far then and write a generalized approach. So I'm taking the text that I wrote down for those 3 scenarios that we talked about. The last one was moving a tower of size 3. Previous to that, we learned how to move a tower of size 2, and previous to that, we moved a tower of size 1. So the obvious kind of general problem we're trying to solve is this notion of moving a tower of size n from one peg to another using the remaining pegs. So I'm going to refer to those pegs as A, B, and C. Okay, so we want to move a tower of size n from A to B using C. All right, now this is meant to be a generalized recursive algorithm, and so we need to state our base case, right? When do we stop, or when do we stop recursing at least, and then kind of put our solution together from there. And that's going to be that very trivial case we talked about before. If we reach a point where we need to move a tower of size 0, then there's nothing to do, right? So we just back up. So I've written that down. Now we want to try and find a generalized way of writing the recursive steps. Now when I look at our description for solving a tower of size 3 or 2, I note that there's a pattern in terms of our first recursive step and the original problem. Specifically, we're moving a tower of size n minus 1 as a step in moving a tower of size n. So let's go ahead and write that down. So we'll move a tower of size n minus 1 from, okay, and then I notice another pattern. I note that the to and using towers get swapped for this step, which makes perfect sense, right? Where we want to get the sub-tower out of the way. So we don't want to put it on our destination peg. We want to put it on that extra peg, and we'll use the destination peg temporarily to get the task done. So in the case of moving a tower of size 3 from 1 to 3 using 2, we start by moving a tower of size 2 from 1 to 2 using 3. And in the same way, even when we were moving a tower of size 2 from 1 to 3 using 2, then for that smaller tower, 2 becomes the destination, and we didn't need to write it because we ended up not using it, but we did have this extra peg 3, that was sitting there. So just because we ignored it doesn't mean it wasn't available, and so our general case holds up. So writing this down, to move a tower of size n from A to B using C, we begin by moving a tower of size n minus 1 from A to C using B. Once that's accomplished, then there's this common step that we see in all 3 of these cases where we move a single disk from the from peg to the final destination, or to peg. So we'll add that here, and you'll note that the peg identifiers are preserved in this case. If we're trying to go from peg 1 to peg 3, then when we move this disk, we're going to move the disk from peg 1 to 3. Or in other words, we want to move a disk from A to B, stated in terms of kind of this general description we're giving in our algorithm. Final step is to move that subtower that we initially got out of the way onto the final peg. And that's consistent, so we'll do that here. We'll move that tower of size n-1 now from C to B using A. And you'll notice that all three towers are just written in reverse order there in terms of their tasks, right? So we're ultimately trying to go from A to B using C. So this last step for this particular algorithm will be to move a tower size n-1 from C to B using A. Now I say it last step, but of course that step is a recursive step. We may need to break it down into smaller towers in order to accomplish it. Let's see this in action. Oh, before I do that though, quick note. Please observe what happens when n, or the size of the tower, is simply 1. Right? Our first step then becomes to move a tower size n-1, which is a tower size 0. So that becomes our base case, and that's what we want because we end up with simply moving the disk from 1 to C, which is, essentially, how do I say this? I'm tripping over my tongue. What I'm getting at is that this algorithm becomes our description to the solution for moving a tower size 1 when n equals 1, which is what we would expect. Okay, let's do a walkthrough of this. So again, we're trying to move a tower of size 3 from 1 to 3. I'm going to place our algorithm in the bottom left corner here, the description of it, so that I can just kind of walk through following it and trying to find the solution. All right, now I'm going to use kind of this pseudocode-like syntax here in describing these steps. So the first thing I'm trying to do, right, the first step in my process of decomposing this is to identify that I want to move a tower, and the arrangement of these kind of parameters I've got inside of these parentheses means that I'm moving a tower size 3 from pillar 1 to pillar 3 using pillar 2. All right, and that's the lingo I'm going to use as I try to write these things out. Okay, so according to our algorithm there, then our first step would be, moving a tower of size n-1, moving a tower of size n-1 from A to C using B. So that becomes moving a tower of size 2 from 1 to 2 using 3. Now, that's easy to say, but again, I'm not allowed to move 2 disks at a time, so we recognize the need to recurse here. So I'm going to break that step out, and so this orange arrow is meant to kind of show that there's a recursive call, if you will, happening here, where we're going to have to break that step down further. So moving a tower of size 2 from 1 to 2 using 3, well, we must first then, of course, move a tower of size 1 from peg 1 again to peg 3 using peg 2 as an intermediary. All right, so we see the roles of the pegs being reversed. We see the tower shrinking. This is all good, okay? Once again, we're going to recurse. We're going to break this down a little bit further. We're going to see that moving a tower of size 1 in this manner requires first moving a tower of size 0. This is good. We see ourselves hitting our base case. From peg 1 to 2 using 3. If and when we recurse on that, or try to recursively break that down further, we see that, hey, moving a tower of size 0, that's trivial, we just return. So we pop back, and now we can move to that second step, right, in recursively breaking down this particular problem of moving a tower of size 1, which was simply move the disk, right, from A to B. And so that means moving the disk from from pillar 1 to pillar 3. Now we recognize that's done. We finished the step of moving that tower, but just to be thorough, we might write out the final step of moving that subtower of size 0, which of course requires no steps, and coming back. And finally, we've finished moving that tower of size 1. So now we can, looking at our steps in the lower left there, we can move that disk from A to B. In this case, that means... have I written something wrong here? Nope, I'm okay. Yeah, so moving that disk from 1 to 2, and then finally moving that subtower. Okay, so again, breaking that out. I know this is kind of tedious. That's why we use computers, right? Okay, so we see that we need to move that subtower of size 1. that we had moved out of the way. Now we need to move it to its destination. So we're going to be moving a tower of size 1 from 3 to 2 using 1. Of course, that involves first moving a tower of size 0, which we just bounce back, and then can move the disk from peg 3 to peg 2. Once again, this kind of meaningless recursive step on tower of size 0, and then we can bounce back. So at this point, we've successfully moved the tower of size 2 from disk 1, or from peg 1 to peg 2 using peg 3. And so with that finished, we can now look at moving that bottom peg in this bottom peg. I'm having a hard time moving that bottom disk from peg 1 to peg 3. And then we still need to move that subtower that we got out of the way onto its appropriate peg, and then we'd be finished. So I think you can see the pattern here. So I'm just going to go ahead and write out quickly the steps that I extracted by doing the same thing that I just finished the first time I moved that subtower, and get it out of the way, and now we need to move it onto the final peg. So, if you need to, then go ahead and, slow this down or pause it and study it, but I think you probably have the general idea. By the time we finished recursively moving that subtower, we're finished. Okay, now this is a lot of text, a lot of words. I'm a visual person, and I know that many of you will be too. So let's look at this solution visually. So to do that, we first need to identify the actual movements of disks here, right? So much of this process is actually just recursively figuring out what to do. The only time we're actually moving things are on these steps here where we said to move a disk. So if we round all of those up, beginning with the lowest numbered steps, right? That's going to be, or those, how do I say this? The lowest numbered step where we move a disk is going to be the first disk to be moved, right? So in this case, it's moving a disk from pillar 1 to pillar 3, or from peg 1 to peg 3. And that was at step 5 in the upper right corner there. If we look closely, we see that the next time we move a disk is at step 7, and that involves moving from 1 to 2. And then at step 10, we move from 3 to 2. And then we bounce all the way to the upper left corner where we move a disk from peg 1 to peg 3. And then step 16 involves moving from 2 to 1. 18 involves moving from 2 to 3. And then finally, at step 21, we moved a disk from 1 to 3 before bouncing back up and realizing we were finished. So those are our steps. Let's actually do it graphically, okay? So here are our pegs. There is our tower. And I'm not going to actually draw, the rods sticking up just because it was easier in this case to, do the animation. And so let's walk through these steps and see what happens. So first I need to move a disk from 1 to 3. So we do that. Then from 1 to 2. Then from 3 to 2. And we see there we've now moved that subtower out of the way. Then we'll move from 1 to 3. That was moving that center movement from our initial problem statement, or I guess I should say the first time we recursively broke it down. Then moved a disk from, we did that already, from 2 to 1, which we just did there, and then from 2 to 3, and then finally from 1 to 3, and we're done. All right, so ta-da, we've successfully moved the tower. The important thing to realize here is that we didn't actually have to think much about it. All we did was follow the algorithm that we had designed on the previous slide. All right, so this is well and good. It's kind of a neat solution. It's pretty elegant. It's simple to write down, and once you get your head wrapped around it, it's actually fairly straightforward. But just because something is, shall we say, simple or easy to say, doesn't mean it's simple or easy to do, right? How hard is it to follow this process, or how much work does it take to follow this process as our towers get bigger? And so let's take, that's an interesting question. It's worth asking and trying to answer. So let's look at the complexity of our solution to the Tower of Hanoi problem. And so I'm just going to restate here our recursive algorithm. And if you look at it closely, you recognize the fact that we are solving n by solving the n minus 1 problem. Okay, so that involves, of course, then actually making all of the moves that we have to make to solve the n minus 1 sized problem, plus that center movement where we move a disk. So the number of moves required to solve a tower of size n is the number of moves required to solve a tower of size n minus 1 twice, right? We had to move that smaller tower out of the way and then where it belonged. So 2 times we have to move that tower, and then that intermediate move, so the plus 1. So 2 times the number of moves for n minus 1, or a tower of size n minus 1, plus 1 extra move. So let's just kind of write this out, see what happens. So our trivial case, a tower of size 0, obviously 0 moves. For a tower of size 1, we would take 2 times the previous, the number of moves needed for the tower of the previous size, which is 0. So 2 times 0, and then add the 1, we get 1. That's good. That's consistent with what we saw. Tower of size 2 then would be 2 multiplied by 1 plus 1, which gives us 3. And I don't know if you counted when we solved the tower of size 3, but not surprisingly, we see that it is 2 times 3, which is 6, plus 1, and so ultimately 7 moves. So using this little formula, we can see that if we just added 1 more disk and went up to size 4, it would require 15 moves. Okay, so this is growing pretty quickly. Each time we add a disk, we more than double the number of moves that are required. It's pretty close to doubling. And so hopefully you're starting to see there's kind of this exponential growth happening here where we're multiplying by 2 each time, essentially. And so you've got 2 being raised to a power that is increasing each time you add a disk. So trying to figure out exactly what that relationship is, if we look at tower size 0, we see that that's 2 to the 0, which would be 1, minus 1 moves are required. And if we look at a tower size 1, that's 2 to the first power, which would be 2 minus 1, which gives us 1. And we see the pattern continues. For 2 disks, we need 2 squared, or 4, minus 1, which gives us 3 moves in order to move the tower. So the relationship we're ending up with in terms of the complexity relative to the number of disks n is going to be 2 to the n minus 1. 2 to the n moves minus 1 are required to solve the puzzle. That's kind of nasty, right? That grows really fast. And that's why even just a tower of modest size, 10 or 15, takes quite a few moves to solve. If we're trying to express this in terms of big O, of course, we just drop off that little 1 and we end up with big O of 2 to the n, or in other words, an exponentially growing problem. Okay, so the complexity of this is exponential. Okay, so that was a bit of a mouthful, but hopefully this has helped you to understand this particular problem, but also given you another taste of how we can decompose a problem recursively and find the solution. And then also, just to state it one more time, I think this is a neat example of how something that seems simple, right? The solution to this problem is we're able to state it in just a few small statements there. And so it's deceptively complex when we turn to actually implementing our solution. And so these are all useful lessons for us to internalize. All right, I'm going to leave it there. I hope this was of benefit to you, and I will talk to you later.